In this video, we're going to talk about the buck converter circuit. So let's draw the schematic of the circuit. The first thing we need is a voltage source, and we're going to use a battery for that. Next, we need a switch, which we'll call S1, and parallel to the battery, we need a diode. And then we need an inductor and a capacitor. The purpose of the capacitor is to maintain a relatively stable output voltage across the load resistor. So this is going to be RL, C, L, and D1. Let's use a 12-volt battery in this example. So this is the buck converter circuit. This circuit works by reducing the voltage at the input. Now, there are a lot of other circuits that can reduce the voltage, such as a voltage divider circuit using two resistors, or even Zener diodes and linear voltage regulators. You can use them to not only reduce the voltage, but maintain a constant output voltage as well. But those types of devices, they reduce the voltage by dissipating power as heat. This circuit reduces the voltage not by dissipating power as heat, but by stepping up the current. And so that's one advantage of the buck converter circuit. It can decrease the voltage while increasing the current. Now let's talk about how this circuit works. So first, let's close the switch. When S1 is closed, current will flow from the battery to the circuit. Let's call the current that flows through the inductor IL. As IL increases, the magnetic field in that inductor will increase, it will expand. And while that happens, the inductor is basically storing energy. It's absorbing energy from the circuit and storing it in its magnetic field. Now, while it's storing energy, the polarity across the inductor is as follows. So notice that the inductor reduces the voltage that is seen by the load resistor. So let's say that at some instant of time, the voltage across the inductor is 5 volts. The voltage across the load resistor is going to be the difference between these two voltages. So in this case, it's going to be 7. So when this switch is closed, the voltage across the inductor is the difference between the output voltage across the load resistor and the input voltage of the battery. And in this way, the buck converter circuit reduces the voltage of the circuit. So when the switch is closed, the inductor absorbs energy, reducing the voltage that is seen across the battery by the load resistor. So now let's talk about how this particular circuit increases the current. By the way, when current flows from the battery through L1, it also charges the capacitor, and current also flows through the load resistor. D1 right now is in reverse bias mode, it's off. Current is not going to flow in this direction through D1. So just keep that in mind. Now let's open the switch. Let's see what's going to happen. When the switch is open, the current that is flowing through the inductor will begin to decrease. And as that happens, the magnetic field will begin to collapse. The magnetic field across an inductor is dependent and proportional to the amount of current that flows through it. Now, as the magnetic field collapses, it's going to induce a voltage with the opposite polarity. So the signs across the inductor is now going to change. The inductor becomes a current source. Now, if the voltage across the inductor is greater than the voltage across the capacitor, it can charge the capacitor during this time. If they're equal, both the inductor and the capacitor can discharge themselves through the load resistor. So nevertheless, current from the inductor can flow through RL, and it can flow back through D1. So when the switch is open and the inductor is releasing its energy, D1 is now active. It's in forward bias mode. So this diode is in the on state. Now let's talk about how the total current increases in the circuit. When the switch is closed, RL receives current from the battery. So we'll call that IB. When the switch is open, RL sees current from the inductor because the inductor is now the current source. When you add the average current from the battery when the switch is closed, and when you add the inductor current, the sum total of these two currents is greater than the average current dished out by the battery over time. In this way, the buck converter steps up the current but can also step down the voltage. Now let's talk about how we can calculate the output voltage. The output voltage depends on two things, the input voltage and the duty cycle. Now the duty cycle is equal to the time where S1 is closed, so you could say when the circuit is on or when the battery is on, divided by the time period. So let's say we were to draw a graph, something that looks like this. Let's use a different color. So let's say that the circuit, this part, that S1 is on for 1 millisecond, but let's say that it's off or that the switch is open for 3 milliseconds. So right here, this would be 1 millisecond, and this value on the x-axis will be 4 milliseconds. So it's on for 1 millisecond, but off for 3 milliseconds. The period is the time for one complete cycle. So the period will be 4 milliseconds. So in this case, it's on for 1 millisecond. One period is 4 milliseconds. So that's 0.25, or a duty cycle of 25%. So that's how you would calculate the duty cycle, and you can control this using a circuit such as the 555 timer. So with this information and with the input voltage, we can calculate the output voltage across the circuit. So the output voltage is going to be the input voltage times the duty cycle, which in this case will be 25% of 12 volts is 3 volts. And so that's going to be the output voltage. Thus, by adjusting the duty cycle, you can adjust the output voltage of the circuit. So let's say we have a buck converter. And let's say at the input voltage, or at the input, we have a voltage of 9 volts. And let's say there's a current of 5 amps flowing to this buck converter. And let's say we're controlling the switch with a 555 timer, and the duty cycle, we're going to say it's, let's use 50%. So the circuit is on half the time, it's off the other half. When I mean on and off, I mean S1. So with this information, calculate the output voltage and also calculate the output current, assuming if this buck converter is 80% efficient. Well, first let's calculate the input power. Power is voltage times current. So if we multiply 9 volts by 5 amps, that's going to be an input power of 45 watts. Now to calculate the output voltage, we know that it's equal to the input voltage times the duty cycle. So since the duty cycle is 50%, it's going to be half of 9 volts. Half of 9 volts is 4.5 volts. Now, once we know the efficiency of this circuit, we can calculate the output power. If it's 80% efficient, then the output power is going to be 80% of the input power. 45 times 0.8 is 36. Now with that, we can calculate the output current. So this is going to be V times I. The output current is going to be the output power divided by the output voltage. So we have an output power of 36 watts, an output voltage of 4.5 volts. So the output current is 8 amps. So we can see in this example that this particular buck converter circuit, it reduced the voltage from 9 volts to 4.5 volts, but it increased the current from 5 amps to 8 amps. So the voltage went up by a factor of 2, but the current went down. Let me take that again. The voltage went down rather by a factor of 2, but the current went up by, if we take 8 divided by 5, the current went up by a factor of 1.6. Now, if this circuit was 100% efficient, the current should have went up by a factor of 2. But chances are, you always have energy losses. This could be energy losses due to the resistive elements of the circuit and also the voltage drop across a diode. But nevertheless, this is how the buck converter circuit works. It can step down the voltage while stepping up the current.